In this presentation we will introduce the concept of passive system and active system. And in particular we will show how we can use the frequency response function to describe an active system. So, two important concepts are introduced, passive system and active system. First of all, a linear passive system is a system with no internal excitation. So there are only external excitation sources. So we have only external forces, F1 and F2 in this case. And if we then observe the response to these two exciting forces, the response in a set of, say, M points, then, as we know from a previous presentation, we can use the frequency response function model to represent this response vector, the responding velocity vector, as the product between a frequency response function matrix and the exciting force vector. So the excitation, or the system input, times the frequency response function, which represents the path or system properties, will give the response vector, or the system output. And as I said earlier, this model describes the response caused by an external excitation, and nothing else. An active system, that's a system that is excited by internal processes. Consider, for instance, that this is a machine with rotating components. Components that interact and create reaction forces, for instance. An unbalanced shaft rotating will create internal forces. That, of course, will produce velocities at our observation points. So how can you generalize the frequency response function model to take this kind of excitation, internal excitation, into account? Well, what you can do is to consider the response due to internal excitation. So you can organize the measured or observed velocity vector from point 1 to point M, and organize them in a vector due to internal excitation, Vs. So S is the internal excitation part of the response velocity vector. Now, if we consider the case that we have both internal and external sources at the same time, what will then become the total response? So now we add the external excitation, F1 and F2 in this case. So the total response in this case is, since we have a linear system, obtained by superposition. So first term here in the total response vector is the internal component with the contribution from the internal sources, Vs, as we have here. And then the second contribution is the contribution from the external sources, given by the product of the frequency response function matrix and the external exciting force vector. So this is the total response if we have a case with both internal and external sources. To summarize here, we have the system input or external excitation vector. We have the frequency response function matrix with passive system properties. We have the source strength vector, as it's called, with active system properties. So the Vs and H frequency response function matrix are the system properties. And then finally we have the response vector, the system output. In this case, this is an example. So if we have this combustion engine, you can see that we have a lot of rotating and translating components that creates internal forces. And these processes, these internal processes will of course create velocities and rotations in the points on the surface of this engine. And that represents of course the internal sources. If we mount this engine in a frame of some kind and the frame vibrates, then of course we will get external excitation on this engine from its interaction with the frame. And the sum, the total velocity response on the surface of the engine will of course be the sum of these two contributions, the contribution from the internal forces and the external forces.